Hi, I'm Jyoti, and I'll be presenting my dissertation titled "Exploring Segmentation, Detection, and Tracking in Videos," advised by Professor Mubarak Shah. About me, I am a PhD candidate here at CRCV. I did my master's from UCF, bachelor's from India. During my PhD, I had the opportunity to intern with Plus AI, Waymo, and SRI. So my thesis lies around the fundamental problem of perception. Now, what is perception? The goal here is to enable agents to see, understand, and act in dynamic environments. So there are two core capabilities: segmentation and detection. Now, segmentation refers to Segmentation refers to partitioning these regions into meaningful scenes into these meaningful regions with pixel level granularity, and detection refers to identifying and localizing these objects using bounding boxes with object level granularity. Now, amongst these core capabilities, the different works in my dissertation is around expanding these core capabilities to temporal space. Now, first core capability, segmentation, expanding it to temporal space would be video segmentation. And the goal would be to assign labels to every pixels in the video. It has different types. Video semantic segmentation, that is assigning label to every pixel. Common pixel based on an object category, like in this case, there is zebra. Then there is video instance segmentation, where we assign label to every pixel based on the object instance. So for example, here, each of these zebras have different labels. Then there is video object segmentation, where we assign label to every pixel for a particular object instance. Now, which is the object instance of preference here is usually predefined in the first frame of the video. Now, the next core capability that we have is detection, and detection across time would be tracking, right? So, as I mentioned to you before, tracking comprises of two steps: object detection followed by data association. Object detection is identifying objects of interest using bounding boxes. Then data association is, given those objects of interest, we are trying to generate trajectories across time steps. So the goal here is to maintain consistent identities of objects across frames. So detect the object and also consistently track it as the same ID. That's the goal. So to give you a brief overview of the roadmap for this dissertation, the first task is on video instance segmentation, where the goal is to eliminate the constraints of fragmented architectures. So to avoid that, what we do is we introduce a unified end-to-end framework for video instance segmentation. The second element is we transition from a supervised version to self-supervised version. The goal is to reduce the limitations of heavy annotation dependency, and specifically in video object segmentation. Next, the two works paper that the previous works that I mentioned is where we do task in 2D space. Now we transition to 3D understanding. So in this task, what I'm trying to do is introduce joint detection and tracking in LiDAR point cloud data. Furthermore, in the next task, what I try to do is I try to generalize this across unseen categories and viewpoints. So transition from closed to open vocabulary, specifically open vocabulary object detection in aerial imagery. So the first work is on video instance segmentation, published in ICPR 2022. Second is on self-supervised video object segmentation in CVI 2024. The third is on joint detection and tracking in 3D point clouds, ICRA 2023. And the final work in the series is on open vocabulary object detection in aerial imagery. Now let's deep dive into the first work, which is on video instance segmentation, published at ICPR 2022. Now, the motivation for this work is that conventionally, video instance segmentation is treated as a region proposal-based correspondence estimation, which is a top-down approach. How that works is, given a set of video frames, we pass it through region proposal network, generate region proposals. Then there is correspondence that is established across time steps. Now, this is a cumbersome disconnected training task, which heavily relies on this standalone external region proposal network. Hence, it is suboptimal. Also, these tend to be frame-based techniques that fail to capture joint spatial and temporal information. So what is of interest to us is the bottom-up approach instead, where video instance segmentation is treated as a spatial temporal pixel embedding plus grouping task. What I mean by that is, given a set of input frames, we pass it through a single stage network, generate video instance segmentation. This is end-to-end trainable, and also we leverage the temporal context by encoding the video sequence. So in this case, what we do is we introduce VIS as a tagging problem. So what is tag and what is this tagging problem? So given a set of input frames, here it is evident to us that there is a background and then there is an animal in the foreground, right? So what we are trying to predict is these tags. What are tags? Tags are these learned embedding values that act as a soft ID for grouping these object instances. So they tend to range from within a range of 0 to 1. But the goal here is not to have the highest value. The goal here is to have a consistent value of this tag for one object instance. That is the whole idea here. Why do we need that? So that at some point we can threshold it over those tags to identify different object instances. That's the whole idea. So the approach is as follows. We have our input images. The goal is to generate these instance tags. And as an auxiliary task, we also generate these semantic segmentations. Now let me go into the details of the approach. How we do it is, given a set of input frames, like 32 frames in this case, we pass it through a ResNet 2 plus 1D encoder with embedded location encodings. This is the resultant output is further passed through spatiotemporal attention block to generate these bottleneck layers and thereafter pass through these bottleneck layers. The resultant output from the bottleneck layers is passed through tag generator, and this generates the instance tags. In addition to this, the resultant features from the tag generator is also passed through these tag attention blocks. Additionally, a residual from these bottleneck layers is passed through self-attention. The resultant output from these two, tag attention base layer and self-attention layer, is concatenated and passed through the decoder layers to generate the semantic segmentation mask. We have two losses in this case, a tagging based loss and a cross entropy loss for the semantic segmentation. Now let me dive into the attention blocks that are important to us in this case, specifically spatiotemporal attention, tag-based attention, and self-attention. Before getting into the nitty-gritties of these attention, let me give you some basic details about the variations of the attention that are important to us here. There is self-attention, where we have an input embedding of dimensions, say 1, 14, 14 to 56. What we do is we flatten it across height and width. Now, once this is flattened across height and width, we pass it through linear projections, get the query, keys, values. Now, queries and keys we compute a scale dot product over the queries and keys. This is passed through softmax to generate attention maps of 196 by 196, 196 by 196 because 14 squared by 14 squared. That's how it's computed. So we have this attention map. We get the values, we get the averaged weighted version of the value, pass it through linear projection, get the refined attention guided input embedding. Now this is for self-attention. For cross-attention, it is different in the sense that the queries and values come from different embeddings. That's pretty much the difference, rest everything remains the same. What is of interest to us is the spatiotemporal attention component because we have temporal inputs that we are looking at, right? So instead of having one input frame of 14 to 56 dimension, we have 32 such frames. Now, since we have 32 such frames, we flatten it across time, height, and width. That basically means that we have an input embedding. We are not just attending to itself, but it is also attending to all the time steps across. Now, once we do some form of linear projection, we get various keys. This is pass through softmax to generate the attention map. Now, if you see here, the attention map did explode, right? Now, in our case, we have some tags which are of dimension 112 by 112. At that point, this explosion is not something which is affordable or feasible for our computation. So instead, what we do is a factorized version of the spatiotemporal attention. Now, this is This is very similar to the one used in Timesformer, and we concurrently worked on it as they did around 2021. How this works is given a set of spatiotemporal embeddings. We split it into spatial component and temporal component. Now, and the attention is computed in a disjoint fashion across these individual components. So that's why there is no explosion of attention maps. Finally, we broadcast the temporal component, and we thereafter do an element-wise addition across the spatial and temporal component to generate the final refined attention-guided spatiotemporal attention features. Now, in terms of our attention modules, getting back to it, we have the spatiotemporal attention. The input to it is from the resonant encoder. However, this is temporal in nature, so we use the factorized version of it. Next, we have tag-based attention. The input to this is the resultant output from the tag generator. Now, since this is also temporal in nature, we use the factorized version of it. Now, self-attention is conventional, no temporal component, so we use the traditional self-attention, that is this. In terms of losses, we have two main losses. One is cross entropy loss, which is the traditional loss on semantic segmentation head. And then there is the tag-based loss, which has, so basically overall we have two losses, tag-based and cross entropy loss, and tag-based loss in itself has 4 components. Now, in terms of, let's get into the details of the 4 tagging loss components. To understand that, we'll first go through something called an element called as HN. Now, what is HN? It is, so this is what our some tags look like in terms of the prediction tags, right? What is HN? It is the mean of all the tag values for a given object instance. Now, this mean is used in our various loss components, which is L spectra. L spectra, what we try to do is we try to pull together all the tags belonging to a single object instance. And L spectra is where we are trying to push away the tags belonging to different object instances. Similarly, we do the same thing across temporal space as well. Pull instance tags belonging to same instance in temporal space, and push away instance tags belonging to different instances also in temporal space. So this is a cumulative sum of the 4 elements, and overall we have tagging loss and the cross entropy loss. In terms of quantitative results, we have state-of-the-art numbers on YouTube VIS, we have state-of-the-art numbers on Davis. In terms of qualitative results, we are interested in the 2 heads. There is an instance segmentation head, and then there is a semantic segmentation head. Let's first look at the instance segmentation head output. Instance segmentation head will have each of these objects will have separate IDs. Now here, if you see specifically, we try to look at instances which are already pretty well separated, right? So if you see here, and these for these ducks, the predictions are pretty good, very well separated, so seems to do a pretty reasonable job. Similarly for these animals in the case. Next, we were interested in looking at qualitative results on video instance segmentation for closely packed instances. Closely packed instances in this case, like for example, this person trying to clean this animal, if you see it, there is a pretty good overlap between the two, but still the ridges of the person's fingers are pretty well predicted. So that means it does a pretty reasonable job there. Again, here in case of this guy playing tennis, the racket pretty much overlines with the person's frame, but still it is identified as a separate instance altogether. So it does a pretty good job. Next, we have qualitative results on the semantic segmentation head. Now here the semantic segmentation head, the objects belonging to same class are categorized as with the same label. So that's why both these ducks are pretty in the same color, which is purple. So here, if you see, we have pretty good results on in both the samples. Next, to summarize, we provide a bottom-up VIS approach that eliminates any training complexities and leverages motion cues. This is done by introducing spatiotemporal tagging loss, which generates well-separated tags for us for the object instances. And we also introduce tag-based attention that reinforces this grouping when doing feature aggregation. As a byproduct, we also have video semantic segmentations, which can serve as a prior for other independent tasks as well. So this concludes, here we conclude with our first chapter on video instance segmentation. But this itself has a lot of limitations. That is, it has high annotation cost because these pixel level video masks are expensive and it's not practical to scale it. There are also video level challenges. That is, there is occlusion, distractors, small objects, which is very difficult to annotate to start with. So that is why there's a need for self-supervision, and which is a reasonable thing to do because there are temporal cues and occlusion cues that can be used to learn these representations without labels itself. So given the limitations in this work, we introduce our second work, which is self-supervised video object segmentation, published in CBIE 2024. Here we use cutout for self-supervision. So what cutout does is it enables general purpose contextual representation. How is that done? Is we introduce these cutouts and we try to predict the content from missing content from partial information. That's what we try to do. That's how the whole learning takes place. This is the premise for the work on MAE, which was published in 2022. We did it before that, but our paper took a while to get published, and that's why we did not get the necessary traction for this work. Okay, now getting on to the approach, specifically the self-supervised training approach. This is what it looks like. Now, here, let me get into schematic details of this self-supervised training. What we do is, given a current frame, we pass it through the encoder, generate the query. Past frame is also passed through an encoder, generate the keys. Now we compute a scaled dot product between the keys and the queries, or have a softmax over it. Thereafter, to generate the attention maps. Now thereafter, here if you notice, the values are from the past frame with a cutout introduced in it. Now this is passed through encoder to generate the values. The weighted average of the values is passed through a decoder to generate the reconstructed frame with cutout for the given time frame. And this is our output. In addition to this, we also predict these tags. Now, these, in comparison to previous tags that we had, previous tags were associated to instances. This is associated to those cutout regions. So we also have some temporal context that we introduce here. In this case, we introduce past frames from without cutout as well. We introduce past frames with cutout. In addition to this, we also intend to focus on the spinner object details. So we introduce something called a zoom in module. Now what zoom in module does is, given in a single forward pass, we randomly pick one of the timestamps and we try to introduce various zoomed in variations for that frame. That's how we bring the zoom in module in this context. In terms of losses, we have two losses. One is reconstruction based loss, which is simple loss between the actual and predicted cutout regions. Then there is a tagging based loss. Now tagging based loss here focuses on separation between the cutout region and the non-cutout region, and that is responsible for foreground background separation. Okay, now in terms of inference, here given that we have already trained using that self-supervised methodology, what we do is, given a current frame, pass it through an encoder, generate the query. Given the past frames, pass it through the encoder, generate the keys. Now, these queries and keys we compute a scale dot product over it, softmax it, get the attention now. Now, if you see, this is about learning the correspondences. Correspondences as in how the goal is to be able to identify how much of the current frame corresponds to what aspects of the different past frames. And this correspondence has already been learned in our self-supervised setting. Given that understanding, what we do is, during inference, we pass the pass segmentation mask as our value, and the weighted value is then passed through a decoder to generate the predicted mask in the current frame. So basically what it does is, since we understand this correspondence, give it the past segmentation mask and see what the current prediction mask looks like. That's the whole idea here. In terms of losses, we have reconstruction loss with cutout. This is simple loss to find the difference between the actual and the predicted cutout region, which is done across time steps. In addition to this, we have the tagging loss. Now, this here, we again have an element called age. Now, this age Previously, it was associated to object instances. Here, this H is associated to the cutout region. So how we use this H here is our first clause, which is LRP, where we try to bring all the tags belonging to that cutout region closer to each other. And then we have LCP, where we are trying to push the tags belonging to different regions other than cutout further away. This innately introduces a sense of object background foreground separatability. That's the whole idea. In terms of quantitative results, we check our results on Davis 2017. We first introduce a smaller corpus for self-supervision, which is YouTube was. Then we introduce a larger corpus, which is kinetics. And our best numbers are using ResNet 50 backbone with kinetics as the data corpus for self-supervision. We have state-of-the-art numbers even on YouTube was compared to the other unsupervised variants. In terms of qualitative results, we have three different things that we have basically claimed here. And each of our qualitative results pretty much tries to establish that claim and validate it. So what we're trying to do is we say that we introduce this cutout-based artifacts, and we say that it emulates occlusion. If it emulates occlusion, we try to see that here, now there's this person, lady, she is headed towards the train. Now at some point, she gets occluded by this guy. She comes out of that occlusion, but she's still identified as the same person with the same ID. That means under occlusion scenarios, this approach seems to do a good job. In terms of qualitative results, we next look into object background separatability, because we claim that our tagging based loss is responsible for object foreground background separation. Now, if that is the case, here in this sample, these shapes tend to mix pretty well with the environment that around those. Also, these adjacent shapes also pretty much have pretty high similarity if you see. But still, the resultant output, you see that it's not only identified as an object, but also consistently identified as the same object throughout the sequence. So the object background separatability is also pretty good. In terms of qualitative results on small objects, we say that we have a zoom-in module, which is responsible for fine-grained object performance. Here we see that there is a conductor leading with some hand gestures. You will see that when we predict, we have pretty good prediction for even fine movements that the conductor performs. So which again satisfies our claim about introducing the zoom-in module. To summarize, we have a self-supervised video object segmentation that eliminates need for any expensive annotations. We introduce cutout page reconstruction, which simulates occlusions. It is pretty much an early variant of ME. We introduce tag-based prediction that enforces object background separation. Then there is zoom-in views, which captures the fine details for small objects. And we show superior performance in Davis 2017 YouTube was datasets. Now, this concludes our second work on self-supervised video object segmentation. Now, all these works have been in 2D space. Now we intend to move to 3D space, primarily because we are interested in real-world scene understanding. And we need to extend 2D pixel level region understanding to 3D geometry and physical space. But when we do this, we need to ensure that and see that if we really need the kind of fine level grained reasoning that we were doing in object segmentation, because there's an option we go for video object segmentation, or we go for detection and tracking when we move to this space. The reason we need to figure that out is because we need to balance between accuracy and time, memory, space compute. Primarily because video segmentation tends to have heavy time memory requirements, and so does 3D data. So that is something we need to balance. Given this understanding, our next work is on joint detection and tracking in 3D point cloud, and this was published in ICRA 2023. So the motivation here is RGB data gives us appearance information, while LiDAR data gives us depth perception. And given this fact, it therefore is extensively used in autonomous driving and assisted robotic tasks. What is of interest to us here is tracking multiple objects in 3D point clouds. That basically refers It's a two-step process comprising of object detection, that is identifying objects of interest using bounding boxes, and data association, that is given the objects of interest, you are trying to generate trajectories across time steps. Now, this is done through affinity estimation, this component. Now, affinity estimation is important to us, and I'll be discussing it in more details in the upcoming slides. Now, okay, since it's a two-step process, what happens is if we have subpar detections from the first step, usually our tracking performance tends to be pretty bad. Also, LiDAR data in itself is characterized by challenges. It has a lot of data sparsity, then there is uneven sampling density. That is closer to the sensor, you'll have a lot of information. Further away, it will be very sparse. So, introducing simple affinity estimation can lead to noisy correspondences with LiDAR data. So that is why we need to improve this affinity estimation. Now, what is affinity estimation? Affinity estimation, so say for example, we have these two consecutive point cloud scans. What affinity estimation does, it establishes this correspondences across these point cloud scans. These regions are similar to the regions in the next scan. So definitely that is how it should have a good correspondence, right? Now, this is done using computing a matrix, which is called as affinity matrix. Now, how do we compute this affinity matrix is what I'll be discussing in the next slide. So, given a set of consecutive point cloud scans, say we pass it through some encoder, generate these feature tokens. Now, on these feature tokens, we compute, we do a cosine similarity across these feature tokens to find the, to generate this affinity matrix. Now, in this case, these nodes represent similarity. A hollow node would mean no similarity. One with a lighter version of pink would mean low similarity. And the one in darker version of pink would mean high similarity. So this is how our general affinity matrix would look like. Now, in this case, for example, we have done a simple form of affinity estimation. So if you see some of these objects, areas correspond to accurately correspond to the areas in the next consecutive frame. However, there are some which seem to have some missing correspondence problem, which is again because of this low similarity that is highlighted in pink. Now, this can happen because LiDAR has an intrinsic problem of the data is sparse. Every time you collect data, some of the elements might go missing. So that is one of the reasons why this results in such noisy correspondences. Now, our approach here, what we try to do in our approach is given a set of input scans. We are trying to get the detections and also track it across time steps. That is what we are trying to do here. Let me get into the details of the schematics. Given the set of point cloud scans, we try to do detection and segment and tracking across time steps in an end-to-end framework. How we do that is given these point clouds, we pass it through a transformer encoder, generate these feature tokens. We apply cosine similarity on these feature tokens to generate these affinity matrix. The affinity matrix is what gives us these correspondences, right? Now, we introduce attention. Attention is unique here in the way that it is not applied on the feature tokens, but it is applied on these affinity matrix because that is what we are trying to improve. We have self-attention and cross-attention on these affinity matrix that I'll discuss in the next slides. And finally, we get a refined affinity matrix. In addition, we have these network heads, which predict the bounding boxes, that is the center and the bounding box dimensions, and a tracking offset. Now, the tracking offset gives us the displacement of these objects across time steps. So finally, the prediction from each of these network cells is collectively used to detect and track these objects. In terms of losses, we have forward association loss here, and we have L1 losses on these bounding box centers and dimension sizes. Now, this is the overall general approach. Now, I'll specifically talk about this attention-guided refinement module. So, the attention-guided refinement module, conventionally, attention would have been applied on these feature tokens. But in our case, we don't do that. We use the attention on these affinity matrix that are generated, primarily because we are trying to refine those correspondences. We are trying to get good correspondence across time steps. Now, what this attention tries to do is it tries to suppress these erroneous similarities. That is what the attention is trying to do, right? And how it does it is by seeking a consensus with global context. So it sees that, okay, some of these regions seem to have really high similarity. There is a neighboring region which seems to have some missing data, but maybe because of that global context, it has that understanding that probably it also needs to have a good higher similarity. That's how it boosts these light pink to the darker pink version and establishes better improved correspondences. Now, in terms of attentions that we use, we have self-attention, which is applied on the individual affinity matrix, where Q and value comes from the same affinity matrix. And then we have cross-attention, where we apply it across affinity matrix, where our query and value query and key come from different affinity matrix. In terms of losses, we have three losses. One is forward association loss. This basically helps us establish those correspondences. So here, this is the predictor affinity matrix, and this is the ground truth. Then we have L1 loss on centers, and we have L1 loss on the dimension sizes for the bounding boxes. And the final loss is an weighted sum of all the three losses. In terms of quantitative analysis, we have state-of-the-art numbers on Waymo dataset, where without the need for any external detector or complex post-processing. We also have comparable results on JRDB pedestrian dataset and state-of-the-art numbers on Kitty validation set as well. In terms of qualitative results, we try to look at diverse conditions. One is long duration tracks. The goal here is not only to detect these objects, but detect it as the same object throughout. So that's what we are trying to do. It is consistently maintaining the ID. Next, in terms of occlusion scenarios, now here we look at this object, which is 109. It enters the occlusion, comes out of occlusion, is still identified as an object with the same ID. So it does a good job with the occlusion scenarios. Then in terms of fast moving sensors, even if the sensor is moving pretty fast, it still detects and tracks objects efficiently. Then in terms of static sensors, here we see again the detection and tracking is pretty reasonable. To summarize, we introduce an end-to-end 3D point cloud detection, joint detection and tracking algorithm, which does not have any need for external object detector or post-processing. But we introduce attention guide affinity refinement to do this, and it does that by capturing global context across affinities. We show competitive performance on Waymo, JRDB, and Kitty datasets. Now, this concludes our work on joint detection and tracking in 3D point clouds. Now, this work focused on detection and tracking. But detection in itself as a standalone task is also of relevance to the research community. So our next work specifically looks into detection task. And specifically what we try to do is we try to transition from closed to open vocabulary. What I mean by that is, like, traditionally closed object detection is trained on a fixed set of classes. That is a closed vocabulary. Adding these new classes can be extremely time consuming, inflexible, and expensive. So open vocabulary object detection allows us to model these and to introduce a model that can identify objects in unseen classes. So that's the whole goal here. And in order to achieve it, this is our next work in the series, which is on open vocabulary object detection, aerial imagery. Before dwelling into the details of aerial representations, let me give you some context about difference between aerial and ground representations. So usually we have abundantly trained, pre-trained models available for ground view open vocabulary object detection. These are predominantly available, but it is not as easy to transfer these capabilities to aerial view tasks. Now, to understand how ground view open vocabulary detection primarily works, what is done in, now this is about just ground view open vocabulary object detection. How it is done is we have an image and text encoder that is contrastively trained with abundantly available ground view image text classification pair. That's how they pre-train the modules. Now, in order to transfer these capabilities to object detection task, what is done is the token pooling layer is removed, and this is replaced with an lightweight classification and detection head. Now, this is ready for open vocabulary ground object detection and ground view. So, primarily, fine tuning is done with limited available data on specifically in these components. Now, this is the same approach we use for fine tuning on aerial imagery, just that the data is aerial in nature. But the problem, okay, now let's talk about, can we use these ground view open vocabulary object detection module as is in aerial view object detection? This is what our results look like when we try doing it. Now, there is extremely poor localization, which is natural because the viewing angle changes significantly, right? And also, we have these small objects in aerial view which need extremely fine-grained feature information. So we understand this. So what if we actually fine-tune that component with aerial data? In that case, we see that the localization problem is pretty much solved. But there is a pretty significant class mismatch. Like something which is motorboat will appear as a fishing vessel that is how the classes match. So there is a pretty predominant class mismatch in this case. So what is the problem here? The problem is that the ground view models were trained extensively on ground view images. But when we do aerial view fine tuning, we don't necessarily leverage those pre-trained embeddings. How can we fix this? We can fix this by introducing aerial and ground view alignment. Now, let me get into some more details about what this alignment is. Now, when ground view was contrasted pre-trained, it does something like this. It creates a joint embedding space for image and text. Basically, here, when images and text belonging to same classes are typically close to each other. And in a well-trained image text joint space, you can effectively use these embeddings interchangeably. This is important to understand. Now, when we do aerial view fine tuning, what we do is this. We introduce aerial view embedding to this existing joint space between ground and text. But given the limited nature of the data that aerial view has, the alignment is not as good. So what we do is we introduce cross-view open vocabulary embedding alignment here. That what we try to do is we try to leverage this existing ground view embedding text embedding space, and we try to maximize the similarity between the ground view and aerial view image embeddings, and introduce a multi-instance association between the aerial view and text embeddings. So that is how we are trying to bring it closer to the existing embedding space. So what it naturally does is something like this. It introduces a cohesive shared space between aerial, ground, and text embeddings. This is the whole goal here. So this is what our approach looks like. So generally what our intention is, given an aerial view imagery, we should be able to predict the object detections in an open vocabulary setting. So getting into the details of the schematics, given an aerial view imagery, we pass it through a vision encoder, generate aerial patch tokens, pass it through a bounding box head to generate the object detections. Now we have a conventional bounding box regression loss here. This setting in itself would be general object detection setting. But we are not interested in a closed vocabulary setting. So we introduce some text. How do we do that? We introduce some classes, pass it through text encoder, and then have a text conditioned classification loss. Now, this would be a conventional open vocabulary object detection setting. But as I mentioned to you previously, this does not fall in that cohesive embedding space well. So we need to introduce some additional components. How we do that is we introduce the ground view images, pass it through a vision encoder, get the corresponding detections such that we are able to map these ground view embeddings well with the aerial view correspondences. And we use our cross-view contrastive loss to do that. Similarly, so now we have that component where we bring ground view closer to aerial view. Now we intend to do that similar thing for text as well. To do that, we have to increase the corpus of the text that we have. Given the classes, we pass it through ChatGPT, generate a huge text bag, pass it through text encoder, and once we have the features embeddings from the text encoder, we use the multi-instance contrastive loss to bring these text embeddings closer to the aerial view embeddings. So this is the general overview. Now in this case, we have this aerial data, but we need some additional alignment data that so as to align all these components. And what is that we need is we need aerial view to ground view correspondence data. We also need aerial view to text correspondence data. How do we generate those data elements? Is we first let's look into the how do we generate aerial ground object detection correspondence data. So here, if you see, we have an aerial view data set, say X view in our case. Okay, we have a category car, and we have a ground view data set, which is Elvis in our case, and we have a same category car. Now, if there are common annotations across these data sets, this is a simple positive pair for us. But what happens when our aerial view has some categories like buildings and our ground view does not have those categories? How do we get positive pairs in this case? What we do is we use those ground view images, pass it through our VIT, we pass it with the category information, generate the detections, and use non-max suppression. And this is how we generate a positive pair between the aerial view category and the ground view category. So this is how the whole alignment data is created for aerial and ground view. To give you some numbers in this context, we have our aerial data set, which is XView, ground view, which is Elvis data set. XView has 60 categories. Common categories between the two are 12. For these 12 categories, it is simple extraction of the object detections, which is around 25K pairs. Then there are other 48 object categories where there is no commonality between XView and Elvis categories. In that case, as I mentioned to you, pass through object, the OWL V2, generate these detections, pass it through non-max, eliminate all the detections that are irrelevant. And this generates another 50K pairs for us. Now, this is one such ground view data set. We use another data set, which is in ground view, which is CC or 12 million, and that generates us a total of 300K pairs. So now we have these alignment data pairs. We also need to do some form of alignment data from text point of view. For that, we need aerial text vocabulary expansion. How we do that is given a category in XView, say this is the category. We pass it through ChatGPT, generate its label variations. And this is done across all the 60 object category classes, which generates us another 360 categories. Now, in terms of losses, we have the conventional bounding box regression loss. This is the text condition classification loss. In addition to this, we have these novel contributions, which is cross-view contrastive loss and multi-instance contrastive loss. So as I mentioned to you before, we have the bounding box regression loss and the classification text condition loss, and our cross-view alignment loss, which tries to bring image in aerial view closer to image in ground view, and aerial text multi-instance loss, which tries to bring image in aerial view closer to the text. And our overall loss is a cumulative of all the four weighted losses. In terms of quantitative numbers, we showed zero short transferability across data sets. Something which is trained on XView with our setting can translate to multiple other such data sets in aerial view. We also show SOTA numbers on Visdrone data set. In terms of qualitative results, we see how our model works across diverse conditions. This is in case of maritime environment. Here, it's a sports facility. Here, in case of nighttime conditions. Here, when there are multiple object interactions in urban settings. And then here, when the pedestrians come through varying viewpoints. Like here it is oblique and here it is top view, but our model does a pretty good job at object detection in either cases. In terms of qualitative results on videos, we try to see how it scopes across time steps and does a pretty good job both in oblique view as well as complete bird's eye view. To summarize, we introduce a open vocabulary object detection in aerial imagery, which leverages ground view open vocabulary pre-training. And we do that by introducing cross-view alignment laws that establishes ground and aerial view consistency. And we also introduce aerial text multi-instance association that aligns aerial imagery with the text embeddings. And to do this, we need that alignment data that we generate for cross-view, ground view correspondence and text expansion. And then there is zero-shot transferability across data sets. So this, with this, I would like to conclude all the four works in this work in this dissertation. In terms of future direction, so far we have what I have tried to do is introduce segmentation, detection, tracking across trimmed videos. Now, introducing it across untrimmed videos can be of use to a lot of biomedical imagery imaging tasks. In addition, introducing this to introducing our 3D work to fusion, introducing multimodal fusion in our 3D work by maybe integrating LiDAR camera or radar through bird's eye view fusion can be of use to autonomous driving space. Then extending our aerial ground alignment to additional modalities like SAR, LiDAR, and temporal streams, we can have these advance the multimodal learning specifically in visual grounding tasks. And these are my publications, and thank you for your time. And I would like to answer any questions. Yeah.
Okay.